Yes, there is switchgear that can accommodate your requirements. Key components include an automatic transfer switch, or ATS. This device monitors the output of both transformers and automatically switches to the backup transformer if one fails. Another key component is a circuit breaker or contactor. This component provides isolation and interruption of the power supply. It can be rated for 4000 amps and higher. There are two common configurations. Firstly, a 2-position ATS. This switches between either transformer, but not both simultaneously. Secondly, a 3-position ATS. This switches between either transformer, both transformers simultaneously, or the off position. The benefits of such a system are firstly, redundancy, providing a backup power source to maintain critical operations. Secondly, reduced downtime, allowing for seamless switching in case of a transformer failure, minimizing downtime and production losses. Thirdly, increased reliability. By having a backup transformer, you reduce the risk of power outages and ensure continuous operation. Considerations to keep in mind are firstly cost. Switchgear for such high amperage ratings can be expensive. Secondly, space requirements. The switchgear will require a dedicated space with appropriate ventilation and access for maintenance. Thirdly, installation and commissioning. This requires specialized expertise and coordination with the electrical company. Some manufacturers that offer high amperage switchgear include Eaton, General Electric, Siemens, Schneider Electric, and Schweitzer Engineering Laboratories, or CEL. For your application, a 3-position ATS with a 4000 amp circuit breaker or contactor would provide the desired redundancy and automatic switching capabilities. It is recommended that you consult with a qualified electrical engineer to design and install the appropriate switchgear for your specific needs. Now let's delve deeper into the technical aspects of automatic transfer switches and high amperage switchgear. We'll start by discussing the functionality of each component in detail, then move on to the various configurations and their applications, and finally explore the factors that influence the selection and implementation of these systems. The automatic transfer switch, or ATS, is the brain of the redundancy system. Its primary function is to continuously monitor the voltage and frequency of the power supplied by both transformers. It does this through sophisticated sensing circuits that are constantly analyzing the incoming power. When the ATS detects a problem with a primary power source, such as a voltage drop, a frequency deviation, or a complete power loss, it initiates a transfer sequence. The transfer sequence involves several steps. Firstly, the ATS verifies that the detected fault is genuine and not a transient event. This is often accomplished by setting time delays and voltage thresholds that must be exceeded before a transfer is initiated. Secondly, the ATS isolates the faulty transformer from the load. This is typically done by opening a set of contacts or a circuit breaker associated with the primary power source. Thirdly, the ATS closes the contacts or circuit breaker associated with the backup transformer, connecting it to the load. The entire transfer sequence is designed to be as fast and seamless as possible, typically occurring within milliseconds or cycles of the power line frequency. This rapid transfer is crucial for minimizing downtime and preventing disruptions to critical equipment. The circuit breaker or contactor plays a vital role in isolating and protecting the power system. A circuit breaker is a mechanical switching device capable of making, carrying, and breaking currents under normal circuit conditions, and also making, carrying for a specified time, and breaking currents under specified abnormal circuit conditions, such as those of short circuit. A contactor is similar to a circuit breaker but is typically used for more frequent switching operations. It is an electrically controlled switch used for switching a power circuit, similar to a relay except with higher current ratings. In the context of high amperage switchgear, these devices are responsible for isolating the transformers from the load during a fault condition and for providing overcurrent protection. They are typically equipped with sophisticated protection relays that monitor the current flowing through the circuit and trip the breaker or contactor if the current exceeds a predetermined threshold. These protection relays can be configured to provide various types of protection, such as overcurrent protection, short circuit protection, ground fault protection, and differential protection. The choice between a circuit breaker and a contactor depends on several factors, including the frequency of switching operations, the level of protection required, and the cost. Circuit breakers are generally more robust and provide a higher level of protection, but they are also more expensive. Contactors are less expensive and are suitable for applications where frequent switching is required, but they may not provide the same level of protection as circuit breakers. Now let's discuss the two common configurations of automatic transfer switches. Firstly, the two-position ATS. In this configuration, the ATS can switch between either transformer, but not both simultaneously. This is the simplest and most common type of ATS. It is suitable for applications where a single backup power source is sufficient to meet the load requirements. The two-position ATS typically has two sets of contacts, one for each transformer. When the primary power source is healthy, the ATS closes the contacts associated with the transformer, connecting it to the load. If the primary power source fails, the ATS opens the contacts associated with the faulty transformer and closes the contacts associated with the backup transformer. Secondly, the three-position ATS. In this configuration, the ATS can switch between either transformer, both transformers simultaneously, or the off position. This type of ATS is more complex and is used in applications where parallel operation of the transformers is required or where it is necessary to isolate the load from both transformers. The three-position ATS typically has three sets of contacts, one for each transformer and one for the off position. When the primary power source is healthy, the ATS closes the contacts associated with that transformer, connecting it to the load. If the primary power source fails, the ATS opens the contacts associated with the faulty transformer and closes the contacts associated with the backup transformer. If parallel operation is desired, the ATS can close the contacts associated with both transformers, connecting them to the load in parallel. The off position is used to completely isolate the load from both transformers, which may be necessary for maintenance or testing. The benefits of using an automatic transfer switch and high amperage switchgear are numerous. Firstly, redundancy. This system provides a backup power source to maintain critical operations. In the event of a transformer failure, the ATS automatically switches to the backup transformer, ensuring that the load continues to receive power. This redundancy is essential for applications where downtime is unacceptable. Secondly, reduced downtime. The seamless switching capabilities of the ATS minimize downtime and production losses. The ATS is designed to transfer the load from the faulty transformer to the backup transformer as quickly as possible, typically within milliseconds. This rapid transfer prevents disruptions to critical equipment and minimizes the impact of the power outage. Thirdly, increased reliability. By having a backup transformer, you reduce the risk of power outages and ensure continuous operation. The ATS and switchgear are designed to operate reliably for many years, providing a dependable backup power source. The system also includes protection features that prevent damage to the transformers and the load in the event of a fault condition. Now let's talk about some considerations that need to be taken into account when implementing an automatic transfer switch and high amperage switchgear. Firstly, cost. Switchgear for such high amperage ratings can be expensive. The cost of the system depends on several factors, including the size of the transformers, the type of ATS, the level of protection required, and the installation costs. It is important to carefully evaluate the cost of the system and compare it to the benefits of redundancy and reduced downtime. Secondly, space requirements. The switchgear will require a dedicated space with appropriate ventilation and access for maintenance. The size of the switchgear depends on the size of the transformers and the complexity of the system. It is important to ensure that there is enough space to accommodate the switchgear and that the space is properly ventilated to prevent overheating. Access for maintenance is also important to ensure that the system can be easily inspected and repaired. Thirdly, installation and commissioning. This requires specialized expertise and coordination with the electrical company. The installation of high amperage switchgear requires specialized knowledge and experience. It is important to hire a qualified electrical contractor to install the system and to ensure that it is properly commissioned. Coordination with the electrical company is also necessary to ensure that the system is properly connected to the power grid. Finally, let's discuss some manufacturers that offer high amperage switchgear. These include Eaton, General Electric, Siemens, Schneider Electric, and Schweitzer Engineering Laboratories, or SEL. These manufacturers offer a wide range of switchgear products and can provide assistance with the design and installation of the system. In summary, an automatic transfer switch and high amperage switchgear can provide a reliable and cost-effective solution for transformer redundancy. By carefully considering the factors discussed above, you can select and implement a system that meets your specific needs. Let's shift our focus now to the specific standards and codes that govern the installation and operation of high amperage switchgear and automatic transfer switches. Adherence to these standards is crucial for ensuring the safety and reliability of the electrical system, as well as compliance with local regulations. The primary standard governing electrical installations in the United States is the National Electrical Code, or NEC, which is published by the National Fire Protection Association, or NFPA. The NEC provides comprehensive guidelines for the safe installation of electrical wiring and equipment, including switchgear and transfer switches. Several articles within the NEC are particularly relevant to high amperage switchgear and automatic transfer switches. Firstly, Article 230, Services. This article covers the requirements for the service entrance, which is the point where the electrical system connects to the utility power grid. It includes requirements for the size of the service conductors, the overcurrent protection devices, and the grounding system. Secondly, Article 240, Overcurrent Protection. This article covers the requirements for overcurrent protection devices such as circuit breakers and fuses. It includes requirements for the selection and coordination of these devices to protect the electrical system from overloads and short circuits. Thirdly, Article 250, Grounding and Bonding. This article covers the requirements for grounding and bonding the electrical system. Grounding is the process of connecting the electrical system to the earth, which provides a low impedance path for fault currents. Bonding is the process of connecting all of the metal parts of the electrical system together to ensure that they are at the same potential. Fourthly, Article 310, Conductors for General Wiring. This article provides guidelines for selecting the appropriate size and type of conductors for various applications. It includes tables that specify the ampacity or current carrying capacity of different types of conductors based on their size, insulation, and installation conditions. For example, Table 310.16 provides ampacity ratings for conductors in raceways or cables, while Table 310.17 provides ampacity ratings for conductors in free air. The ampacity of the conductors must be sufficient to carry the maximum load current plus any applicable directing factors. Fifthly, Article 408, Switchboards and Panel Boards. This article covers the requirements for switchboards and panel boards, which are assemblies of switches, circuit breakers, and other protective devices used to distribute electrical power. It includes requirements for the construction, installation, and labeling of these assemblies. Sixthly, Article 700, Emergency Systems. This article covers the requirements for emergency electrical systems, which are designed to provide power to essential loads during a power outage. Automatic transfer switches are commonly used in emergency systems to switch between the normal power source and an emergency power source, such as a generator or a battery system. In addition to the NEC, other standards may also be relevant to high amperage switchgear and automatic transfer switches. These include standards published by the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. IEE standards cover a wide range of electrical engineering topics, including power system protection, grounding, and surge protection. ANSI standards cover a variety of topics related to electrical equipment, including switchgear, circuit breakers, and transformers. Compliance with these standards is not only important for safety and reliability, but also for insurance purposes. Insurance companies often require compliance with relevant standards as a condition of coverage. It is therefore essential to consult with a qualified electrical engineer to ensure that the installation meets all applicable codes and standards. Now, let's move on to discussing some of the specific design considerations for high amperage switchgear and automatic transfer switches. These considerations include the selection of the appropriate equipment, the coordination of protective devices, and the design of the grounding system. The selection of the appropriate equipment is crucial for ensuring the reliability and performance of the electrical system. The first step is to determine the load requirements. This involves calculating the total current the switchgear and transfer switch will be required to carry. The load requirements must take into account the continuous load, the intermittent load, and the starting current of any large motors or other equipment. The next step is to select the appropriate size and type of switchgear and transfer switch. The switchgear must be rated to carry the maximum load current and must have sufficient interrupting capacity to safely interrupt any fault currents. The transfer switch must be rated to carry the maximum load current and must be able to transfer the load quickly and reliably. The selection of the appropriate protective devices is also critical. Protective devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. These devices must be properly coordinated to ensure that they operate in the correct sequence. Coordination involves selecting devices with appropriate time current characteristics so that the device closest to the fault will trip first, minimizing the extent of the outage. The design of the grounding system is another important consideration. The grounding system provides a low impedance path for fault currents, which helps to protect personnel and equipment from electrical shock. The grounding system must be designed to meet the requirements of the NEC and other applicable standards. This typically involves installing a grounding electrode system, such as a ground rod or a ground plate, and connecting all of the metal parts of the electrical system to the grounding electrode system. In addition to these design considerations, it is also important to consider the environmental conditions in which the switchgear and transfer switch will be installed. The equipment must be protected from moisture, dust, and other contaminants. The equipment must also be able to operate within the specified temperature range. Regular maintenance is essential for ensuring the long-term reliability of high amperage switchgear and automatic transfer switches. Maintenance should include regular inspections, cleaning, and testing. Inspections should be performed to check for any signs of damage or wear. Cleaning should be performed to remove any dust or dirt that may have accumulated on the equipment. Testing should be performed to verify that the equipment is operating properly. The frequency of maintenance will depend on the environment in which the equipment is installed and the operating conditions. However, it is generally recommended that maintenance be performed at least once a year. In conclusion, high amperage switchgear and automatic transfer switches are essential components of modern electrical systems. By carefully considering the design, installation, and maintenance requirements, you can ensure that these systems operate safely and reliably for many years to come.